Good morning and welcome to what I hope will be the first of our annual Christmas lectures. This morning we are joined by Professor Nicholas Owens, who is currently the Director of SAMS, but has also spent time as the head of the British Antarctic Survey. He's going to be talking to us today about how ice core sampling can tell us about past climates and also about the amazing life that he's had in the Antarctic.
But anyway, so I'm going to tell you a little bit about the Antarctic, some of the things that you can see there, and perhaps how you get there and so on. But also going to do a little bit of science as well on climate change. What is it? Is it real? Because I don't know what all of you think. I imagine there probably isn't anybody here who doesn't think that climate change isn't a thing. But there are a lot of people out there actually who just do not believe in climate change. So I'm going to show you really a lot of some data, some information, some facts that are collected from the Antarctic, and in particular how we can look back in time actually as to what the climate was. And so there's some quite interesting things that we do in Antarctica. And although I'm a marine scientist, one of the things that I'd quite like to try and get across to you is that you can go and do all sorts of different things in science. You don't have to be too worried, really, about what particular thing that you do. So as I say, I did a marine science degree at university and then went on to do a PhD, but I ended up still going to the Antarctic and doing all sorts of interesting things as well. And so while at the beginning, when you're thinking about things to do, you might think that it's really, really important to do a very, very narrow sort of topic at university or whatever. Don't, if that's what interests you, don't be put off by that. That there are lots and lots of opportunities. So, for instance, at SAMS, there we've got 160 people working there, and about half of them have had education after school, all sorts of things, hires as well as degrees and things like that. And probably of those, only about 20 or 30 or maybe 40. So perhaps only about a quarter of the people actually who work as scientists at SAMS actually did marine science. There were chemists there, there were physicists there, there were geographers there, there were all sorts of people there. So don't think that that you're restricted into doing that. So anyway, right, so let's make a start. So you'll recognise this, I hope. Yep, cool. There's Dunstafnage Castle down at the end there. And I was just telling your teachers there that actually I'm very lucky in that actually this is where my office is, right there, looking out at the sea. So that's a pretty cool place to go to work, isn't it, really? Anyway, right, what I'm going to do first of all is show you where the Antarctic is and where the Arctic is. And we need this here, and because a lot of people, and I know you lot are all very bright, aren't you? So the difference between the Arctic and the Antarctic. So the Arctic is up at the top, North Pole right there, and the Antarctic is down at the bottom. So I don't know whether you want to have a play with that. But a couple of things, we're not going to talk about the Arctic, but a lot of the things that we can do in the Antarctic, we actually also do in the Arctic. But what is the obvious difference between those two things, those two places? Anybody spot what the obvious difference between the Antarctic and the Arctic is? They're both very cold. Can you see what there is? So the Antarctic is a continent surrounded by an ocean. Yeah, can you see that? So this is the Antarctic continent. So this is land. We'll come to that in a second. So this is all land, admittedly covered in ice. And the Arctic, primarily, is an ocean surrounded by land. And that makes a huge difference to what goes on there, what lives there. It fundamentally changes everything about those two places. So they're both at opposite ends of the Earth. They're both cold. They're both frozen for most of the time. But the Antarctic is land and the Arctic is ocean. And that actually, we won't go too much into that, but actually that makes a huge difference to actually what happens in both of those places. So when we come to the Antarctic, so here we are This is South America down here. This is the Antarctic now. That's a bit of Africa there. So you've got this frozen, icy wasteland there, and you can read it for yourselves. So it is the highest. So something like the whole of the Antarctica, the average height of Antarctica is about 3,000 meters, and most of that is ice. So over thousands of years, hundreds of thousands of years, the ice has just built up. So you've got this massively high continent. There's lots of mountains in there as well. It's the coldest. So any idea what the coldest temperature in Antarctica is? Close? Anybody want to have a guess? So we had -17 in Braemar last week, which was pretty cold. What do you think the coldest place in Antarctica is? Somebody have a guess. -30. Long way off. -89. So -89, and it was about here somewhere at a Russian research station called Vostok. That was -89. And it's the windiest, and I can assure you that there's virtually a day never goes by when you've not got gale force winds there. The other interesting thing about Antarctica is that actually the continent itself doubles in size in the winter. So this bit here, this is all the land covered in ice. But this lot around the outside here is sea ice, which freezes all the time. So it freezes in the winter. And don't forget, the winter is our summertime. So midwinter in Antarctica is June. So we're now actually in Antarctica approaching midsummer. So in midwinter, it looks like this. That's all ice. And in midsummer, it disappears. And there's what I've got now is a whole series of satellite images that have all been built on top of one another to produce like a little bit of a kind of a movie, really. And hopefully this will work. There we go. So the stuff around the outside are all clouds, but this is all ice. Now just watch what happens. So we're now approaching spring, and you can see it starting to melt, and then it goes really quite quickly. Virtually disappears. And so the whole of the continent, actually, it nearly doubles in size with that sea ice. And that keeps going. So that happens every year. Now, there's quite an interesting story between the sea ice in the Antarctic and sea ice in the Arctic because of those differences that I started out with. But that's all you need to know for now about that. Now, when we come to the ice that we'll come to in a minute, that I'll show you about how we look at what's happened in the past. We're not talking about this sort of ice. This is the ice that on the sea. We're talking about ice that is on the Antarctic continent itself. Now, the interesting thing about the Antarctic like that is that it is just like it's like a Christmas cake. It's solid stuff underneath, but just with completely covered over with like just with ice, just like a Christmas cake and the icing on top. But if you were to take all the ice away, actually what you've got is this really interesting. This isn't a very good photo, I'm afraid, so do forgive me. But what you've actually got underneath all of that is you've got rivers and you've got valleys and you've got mountains and you've got all sorts of just the sort of landscape that you see out here. Just the same. So you've got hills and mountains and so on. But what you've got, though, is you've got something like over a mile thick of ice that is built up over time. So that's quite interesting. And some of the things that some of the work that is being done at the moment is these are meant to represent little lakes. And there are hundreds and hundreds and hundreds of lakes, just like we've got here. And there are experiments going on to drill through the ice and get into these lakes. And one of the things that is thought of is that what is going on in these lakes in here might well be what the life in there might well be the sort of life that exists on some of the moons of our planets that have got icy lakes underneath the frozen surface. So that's quite interesting. Anyway, the thing about the Antarctic is it's a wonderful place for wildlife. And I've got a few pictures here just to, relax you a bit and see all of the wonderful life. And so you've got all sorts. fantastic. These, of course, are what most people think of as the Antarctic. Loads of penguins, especially these guys. You know, this is fantastic. And they really are. This is an emperor penguin, and they stand about this high, actually. They're quite a decent size. And they're pretty vicious as well. You don't want to get too close to them. And a few others here. These macaroni penguins, these are quite cute things. And when they come ashore to breed, they do so in unbelievable numbers. This is a photo of on one of the Antarctic islands of macaroni penguins. Oops. And there are something like 250,000 penguins just in this one rookery, as they're called. So penguin rookeries. And lots of things like this, lots of different seals. These little fur seals, they're really very cute, but they are vicious. And I have to say, going for a walk along an Antarctic island beach is really very unpleasant, because these little things here, and they're only like about the size of a spaniel, maybe a bit bigger, and they are absolutely vicious. So they've got teeth like this. Absolutely vicious, and they will chase you and will bite you, and really quite horrible. These things, leopard seals, are really quite horrible things, and they will attack people in the water. And elephant seals, particularly big elephant seals, a big elephant male will be from about there to about here in length, and are probably about as wide as from there to there, and they are horrible. Well, I won't tell you exactly what they do, but they make lots of horrible noises. They stink. They're really quite unpleasant things. But it's because it's a wonderful sight to see all those things. And of course whales. And so these are the sorts of things you see. Of course you can see all of these. So this is a killer whale. That's a humpback whale there, and that's a minke whale. You can see those obviously just off here, if you're lucky. But you know, the Antarctic is a pretty good place to see them. And I have to say, my favourite of all are the albatrosses, and there's lots of different albatrosses. There are 4 different albatrosses here, and this is the wandering albatross. And you can see there's a little baby sticking out the end there, and those things are quite incredible. I mean, they can actually, there's some tracking has been done, and they will fly completely around the whole of the continent of Antarctica in search of food for their young. And they live for 50 or 60 years, and which is quite remarkable. But one of the sad things about all forms of albatrosses is that they are very susceptible to picking up fishing gear. Unfortunately, there's a lot of fishing goes on around the Antarctic, and they use lots of fishing gear and nets and various other things. And for whatever reason, the albatrosses in particular, they think it's food. And unfortunately, a lot of albatrosses die because they get lots of fishing gear stuck in them, which is really rather horrid. But this is underwater. Fantastic life underwater. And I've got something here that you might be interested in. So you see this? This is a diver here, okay? And you can see this is a sponge. Now, normally, those things are probably about the size of your fist. We've got lots of these types of sponges off here. So if you go snorkeling, or if any of you dive, or just put your head under the water, you can sometimes see these little sponges, and they're only about this big, about the size of my fist. A big one would be about the size of my fist. But down in Antarctica, everything grows to an enormous size. Any idea why they might grow so big? And it's not just those things. I've got something here, which I'll pass around. This is the equivalent of a woodlouse. Okay, you know the little woodlices that you see around the place? Well, that's a relative. I'll pass it round. Do you want to pass that around? So you can see it? No, you don't want to have a look at that woodlouse, right? Go on, pass it round. Any idea why these things might grow so big? Come on, somebody must have a clue.
Someone take a guess.
Say again?
Did someone
Oh, sorry, right. Somebody take a guess. Yes, please take a guess. Okay, so the place is so huge they need to get there. Did you say something? Nutrients. Did you say? Well, nearly nutrients. Well, what it is because the water is so cold, it means it can absorb a lot of oxygen. It can hold a lot of oxygen, right? So those of you who are doing a bit of, I don't know, physical chemistry, the colder the water is, the more gas it can contain. And so in the Antarctic water, which is around about 1 degree centigrade, that's all, it can hold a lot of oxygen. And if you are an animal that takes in its oxygen just by absorption through its body, it actually means, because there's loads of oxygen there, it means you can grow really big. And it's a big advantage to be really big, because it means you can actually take up food from everybody else and so on and so forth. So that's one of the interesting things about the Antarctic, about the science in the Antarctic. The other interesting thing is, as I say, the seawater can go down to about -2 degrees in the bottom, and yet we've got fish here like this. So normally, what would happen if you were sitting around at -2 for any length of time? Your blood would freeze, wouldn't it? Well, these guys, their blood doesn't freeze. This is an ice fish, and they've got antifreeze. They've developed, evolutionary speaking, they have developed antifreeze in their blood, and they can actually go down to about -5 if you had to put them down to and they could live quite happily at that sort of temperature. So that's quite an interesting thing there. And here's a trick. Somebody must know what that is. A polar bear, yes. And guess what? They don't live in the Antarctic. They live in the Arctic. And you'd be very surprised at how many, and I bet you will see some this Christmas. You will probably see Christmas cards where you've got polar bears and penguins actually at the same time. That does not happen. Trust me. Please, 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 trust me that is only in the Arctic. So do not get carried away by the fact that. So polar bears do not live in the Antarctic, and penguins do not live in the Arctic. And the other thing that you need to know is, do not forget when you're spelling Antarctic and Arctic, don't forget that C there. Arctic or Antarctic. I know that sounds a bit daft, but I see it all the time with people who really, really, really should know better. Actually, they forget that C in there. You will hear Arctic. All right, that was the easy bit. Okay, we're going to just start doing a bit more science now. So, can somebody tell me what the greenhouse effect is? I mean, the answer's there, but in your own words, does anybody like to describe the greenhouse effect? So the sunlight comes in and it warms the Earth up. And when you warm the Earth up, then you get a different wavelength of heat that comes back out. So you get the heat after the Earth is warmed up, comes out, and that wavelength is actually trapped by the atmosphere. So you've got the Earth's surface with a layer of atmosphere around the outside, and what is going on in that atmosphere actually traps the heat that is being reflected back out from the Earth. And so you mentioned carbon dioxide. Well, the amount of heat that is actually trapped by this heat that can't escape, a lot of it does escape, but a lot of it doesn't escape. The amount that stays in, that creates the warmth, is dependent on the gases that are in that atmosphere. And there are lots and lots of different sorts of gases in the atmosphere, and some of them are known as greenhouse gases because they increase the amount of heat that is trapped. And carbon dioxide is the one that we all know about. But there's lots of others. Anybody tell me one other greenhouse gas? Will they know that? Somebody would know that. Methane, methane, absolutely, methane is good. Now, Sam's, this is a diversion, okay? Sam's is doing some interesting work on types of seaweed. Some of the seaweed that we can grow in Sam's, and if you feed it to cattle, because cattle produce a lot of methane, if you feed this particular type of seaweed to cattle, it reduces the amount of methane coming out of the cows, which is quite clever, and we're all hoping to make millions out of it one day, but who knows? Anyway, so going back to the greenhouse effect, yep, you've got lots of gases in there, and carbon dioxide is one of the key ones. Now, in actual fact, we need the greenhouse effect. If we didn't have the greenhouse effect, Earth would not be livable on. So the greenhouse effect is not a bad thing. We need it, but what you need is, what we're worried about is what's known as the enhanced greenhouse effect. Too much. So too much of it. And this is the problem that we've got, is that there is too much heat being retained. So what has happened? You should probably all know this. So this is a graph showing the temperature going up since the 1800s, and off it goes like that. That's not, I think, a graph like that you should be pretty familiar with, I would think. And this is the whole point of this global warming. And it's no coincidence, actually, at all, that if you put that same graph and put on there the amount of carbon dioxide, CO2, carbon dioxide, in the atmosphere, look at what's happening. Now, the physics of this is very, very simple, which we don't need to go into the physics of it, but there is absolutely no doubt whatsoever, and whoever you talk to who said, no, it's not happening, you can absolutely say to them, there is no doubt whatsoever that carbon dioxide in the atmosphere actually retains heat. That is just physics. There's no dispute about it.
Can I ask a question?
Yes, please.
It says in the 1940s, it looks like all through World War II, the global temperature was higher.
Was higher.
Is that a coincidence?
No, it was just a coincidence. It was nothing to do with the war. It was just one of those things. Just one of those things. I'll show you something now then, if you're interested in that. This is showing the temperature going back 500 million years, right? So this is this period here, the Jurassic, okay, the dinosaurs. So what this has got, this is a complicated graph. So just if you can just dwell on it a minute, this is today over here, all right? And this is over 500 million years ago. And what is happening here, don't worry about the different colors, that's for a different reason, that they're all different colors. What this is showing is, so this is today's average, this line going across here is today's temperature, and look at what has happened to the Earth's temperature over all this time. And so when people say to you, if they don't believe in global warming, they'll say, oh, but the Earth has always changed temperature. Yes, that's true. Absolutely it has, in ways that we cannot imagine. Look at these huge temperature changes. Massively hot planet to really, really, really cold here over all of this time period. And there's a whole series of lessons to be had, actually really interesting lessons as to explain why all of this has happened. And we know mostly why this has happened. But if we just look at this little period for a minute, so the more recent time, which is I think is quite interesting, so this is now going back. So this is the first Christmas here. So this is 0. So this is BC moving into AD. So the Romans, the Dark Ages, the medieval period, and the Little Ice Age. And so we're about here now. And look at this. This is really interesting, isn't it? How the temperature just over this period in recorded history, how the temperature has changed. So in the Roman times, we had vineyards up here. At least there would have been if the Romans had been here. But there were vineyards in northern parts of Britain during that period. In the Dark Ages, we know it was very, very cold. A big flowering of society in the medieval period actually accompanied that it was really warm. And then we went into the Little Ice Age, and you will have seen pictures of the so-called snow fairs on the River Thames, which, the River Thames froze and all the rest of it. Now, we know why all of this has happened. It's an interesting story. Here's the picture of the sort of thing that was happening in that little ice age period, sort of pictures that you might see. But what I want to do is just go into this picture. So this is 800,000 years now. This is today. This is 800,000 years ago, and this is the temperature now over that period. And what you're seeing here is periods of warm. All of these peaks here are warm periods, and all of these big dips down here are the ice ages. And so over this 800,000 year period, you've got something like 8 or 9 different ice ages going on there. And this was the last ice age, maybe 10, 12,000 years ago. And so we're actually in a warm period now. And so when people say, well, it is a warm period, well, it is a warm period compared with history. But if you look at what is happening to the carbon dioxide, you go, wow, that looks pretty similar. And actually, if you put the two together, sure enough, there is an absolutely a complete correlation between the ice ages coming and going and the temperature. And just out of interest, so this graph goes up to 300. So this is the amount of carbon dioxide in the atmosphere. And this is in this unit, parts per million. So 300 parts per million. So over this 800,000 year period, right? So nearly a million years. For a million years, we've never had anything more than 300 in the atmosphere. That was yesterday's figure. So 416, it'd be off the top of this graph here, be up here somewhere on the same graph. So we have, just in the last 150 years, we have actually taken the carbon dioxide from completely from where it's been for the last million years, completely off the scale. And that is the global warming bit. And if you look at a big planetary scale, pretty obvious the red bits are the warm bits. And so that is what global warming is all about. And it's true that there are certain parts of the world where actually there will be cooling. So it won't be warm everywhere. But the red bits, and particularly in the Arctic and in the Antarctic, are really sensitive. And that's where the biggest warmth is coming from. Okay, so what I want to do, though, is just go back to this carbon dioxide in the past. How on earth do we know that? There weren't labs around like Sam's 800,000 years ago measuring it. So how did we do that? Well, we did it because of this. So this is a picture in the Antarctic. And I don't know whether you can see it. Can you see the striations in there? Okay, well, what's happening there is that the snow is falling, and because it never melts, it just builds up on top of each other like this. Keeps on building up and building up and building up and building up. And until you get these really nice layers. And they don't, and if you go to the right place, then they're completely undisturbed, and you've just got nothing to disturb them. And what they form is like a record of history, what was happening when that snow fell. So the snow falls, it hits the ground, and then it freezes. And then more snow falls and falls on top of that. Now, one of the things about snowflakes that you know about, if you get a snowflake and it falls on your hand, what's one of the things that you notice about it? They're all unique, yep. And it does melt, it absolutely does melt, yep, indeed. Unless it's in the Antarctic, of course, where it doesn't melt. But actually, they're full of air. So if you look carefully at a snowflake, next time you see one, before it melts, just have a look at it, and actually they are full of air pockets. And that's what's happening here, is that what's happening here is as these snowflakes all form into ice, you're actually trapping a bit of the atmosphere at the time that it fell. And what you can do is you can take thin slivers of that, and you see all these little bubbles in here. So this is a piece of ice, a very thin piece of ice. So this is a thin piece of ice full of bubbles of air. And that is a snapshot of the air that was formed, that was in place when that snowflake fell. And so if you can go find ice back in history, then actually you've got a little sample of air that you can measure. And that's exactly what the ice core is all about, and where an awful lot of the science behind what we know about the climate of the Earth and why we know so much about global warming now is because of this type of science. And so I've got some footage of some ice cores that are being collected from the Antarctic. Hopefully this will work. So this is coming out, and here is, so it's a big drill going down through the ice. This is all under the ice surface. You can see this is a lab that's been built in the snow in Antarctica. And a bit like drilling for oil, you just keep on drilling down and down and down and down and down, and you can keep just pulling out lengths of ice and then keep on going down. And you can get down, as I told you, it was about 1.5 miles deep, the ice. And so if you can find somewhere like that, then you've got something like this. So this is an ice core. And you can do all sorts of things. So you can measure it, and you can slice it and get those little thin slivers. Now, doing something like this is not easy. So we're talking about temperatures as low as -89, middle of nowhere, bottom of the Earth, and we've got people working there doing all of these very, very clever technical things. And it's quite a challenge. And so you've got a lot of infrastructure needed to do this. So you've got camps, you've got people having to live there. So you've got cooks, you've got doctors, you've got all sorts of people living there. Lots of different nationalities usually as well. It's not just one. And here is a picture of a typical ice core camp. And these would be, people would be staying there for months to drill the entire depth of the ice. Now, at the moment, the furthest back that we've been able to go is 800,000 years, and that's what I've just been showing you. The hunt is on for what is they call, the oldest ice, where we think, because of the overall thickness, we should be able to find ice that goes back to about 1.5 million years, possibly. And it would be really good if we could do that, because we know from other things that about 1 million years ago, those regular ice ages happened about every 50,000 years. Well, if you went back to that earlier graph I showed you, you can actually see that these ice ages actually speeded up by earlier than that. We absolutely have no idea why that is. So it would be really great to go back to the oldest ice. And it's long past my time going to the Antarctic, but it may well be that some of you here actually can find that oldest ice. How do you do all of this sort of stuff? This is in the middle of nowhere. How do you get there? How do you put all this equipment in? Well, various ways. One of the great things about being the boss of the British Antarctic Survey was I had my own fleet of aircraft, for instance. And so here's a couple. And they weren't flying as close as this. This is a bit of a fix, this photo. But anyway, so this is a intercontinental aircraft. This is a Dash 7, and this is a Twin Otter. And you can see these things have got skis on the bottom. The bigger plane is, you can actually land on what are known as blue ice runways. So this is just pure ice. It's like the ice rinks that you go to. And one of the things you learn very quickly is when you leap out of a plane like that onto blue ice runway, you do so very gently and very carefully. And so you can bring in equipment, and it can take weeks and weeks and weeks of flying in and just unloading equipment like this. In the British case, there is a forward base, and this is a photo of one of the British stations. This is the Rothera station in summer. And this is a place where a lot of scientists spend their time. They work there for many months at the time. Some scientists will stay over winter there as well. And indeed, we've got 2 SAM scientists are on their way to that station right now. They left Britain a couple of days ago, and they're on their way to that station now to do some work out in the mountains. There is a runway there, this is the summer situation, so it's a clear runway, so it's a hard runway like you would see anywhere. And there are hangars, and this is the Dash 7. You can fly from the Falkland Islands or South America in that and land at this Rothera station. It takes about 6 hours. So you've got all of this set up there, which is absolutely fantastic. But one of the really clever things is when these twin otters come in. So this is the plane you see with wheels, but I showed you a picture with the aircraft with skis on it. Well, what we've got here is some footage of a twin otter aircraft, which has got skis, coming into land, actually at one of these bases. But he doesn't land, actually, and unfortunately the film ends, but what actually happens is it takes off again. And it does that 2 or 3 times until it's sure that it isn't going to sink into a crevasse or something. And I have to say, seeing the pilots doing this and being in the planes with them is incredible, because when they come into land and they've got a completely virgin bit of snow, and they make the ski tracks, and they can do that 2 or 3 times, and they land exactly down the same tramways. It's incredible. And they're only about this wide. So let's see if this will work. Now, what you'll hear is a communication between somebody on the ground who's setting up camp. He'd be sitting in a tent, probably, and the pilot. And he's saying, do you want a roller? And that's what this landing and re-landing is all about. So hopefully this will work. Okay.
You want another roller again? Yes, please.
So the yes, please was the pilot. I have to say, one of the best bits of being in the Antarctic is flying around in these things. It's quite extraordinary. In that scenery, it's just amazing. So that's the way in with all of this kit, and so it's quite a feat of logistics. The other way, of course, is you've got to get all of that stuff in to keep the bases open, and that's done by the ships. And this is the newest of the Antarctic ships. This is the Sir David Attenborough. And for those of you who remember, this was there was a competition. That was where Boatface came from. That's what they thought they would call that ship, and you couldn't call it that, could you? Anyway, she's out there for doing her first proper science season right now. And as I say, some of our SAM scientists are actually on that ship now. They've been in the Falklands, and they're actually going to Rothera on the Sir David Attenborough right now. And really, that's all I wanted to say. Hopefully there's something in there for nearly everybody. But if you want to know more, come to SAMS. Come and do a degree with us. So we are part of the University of the Highlands and Islands, and we do a marine science degree, and we have lots of interesting streams in that marine science degree. We have a stream that allows you to go to the Arctic for a year, which is unique to the UK. There is no other university that does anything like that. So you can come and do marine science and have a year in the Arctic if you want to. We cover all aspects of marine science, from little animals to physics, to ice, to oceanography, fish, you name it. We also have just introduced a stream in robotics, where we actually where we teach people how to use underwater robots which is being used more and more these days. And so if you're at all interested in what we offer at SAMS, don't hesitate to ask questions. And it's been really nice talking to you. Thank you very much.